progress.
Good morning, everyone.
Morning.
Today we are going to start section 6.3, volume of revolution. Okay. So what is a volume of revolution? So in section 6.2, we studied the idea of area between the two regions. Today we're moving to volume. The solid of revolution is a solid obtained by rotating a region in a plane around a line in that plane. So let's see what we mean by that. So for example, suppose I take the following region in the plane, this region. That's a region in the plane. And I rotate it around a line in this plane. So I'm going to rotate it around the x-axis. What will I get? Can anybody, I know it's early in the morning, just imagine if I take this region and rotate it. So we're going to get a 3D object. What will I get? Anyone?
Cone.
What?
You said a 3D object, right?
Yeah, because you're going to take it and rotate.
Half a cone then?
Exactly. We're going to get something close to a cone. We're actually going to get a cone. Absolutely correct. A cone. Okay. All right. So that's what we mean by solid of revolution. Let's take another simple example. Suppose I take a triangle, a rectangle. I did already a triangle. I take a rectangle. That's my rectangle. Okay. And I take it and rotate it around the x-axis. What do you think I will get?
Cylinder.
Cylinder. Absolutely. I want all of you to pitch in. So we're going to take it, rotate it. Rotate it. Remember, that's a 3D object. It's an absolutely 3D object this time. Rotate it. We're going to get the cylinder. Okay, and it's a solid. It means the inside here is not hollow. It's an absolute solid object. So in general, we can take actually any region in the plane, any region. Oh, I don't know. Let me take something like that. This whole region, all of it, which is filled inside. So that's the whole region. And we can rotate it around, that I said, the x-axis. And I will get like a ball somehow. So I'm going to get this piece right there. Okay. The goal in this section, the goal is to find the value of the solid. That's really our idea. Goal is find the volume of the solid. Looks definitely a complicated problem. Okay, but it's not. Right, so that's really my idea. Find what is the volume of this. All right, how are we going to approach? What's going to be our strategy? And then we do the math that we need. Our strategy is the following. You don't have to write. I'll just describe a few words, our strategy. Let me take you back to the idea of area. What was our strategy to find the area under a curve? So this is a curve, it's curving, it's not a straight line. To find this area, what was the strategy? Anybody kind of put it in few words? And not integral, actually not integral. What's the correct strategy? It is given by integral. The answer is correct. How did we get to this integral? Exactly. Gonna split the region. No, not two region, into rectangle. Right. The strategy was, it's a complicated region because this is curving. So it's not like a straight line where I can start playing with it. It's just there is a curve. So the idea is to split it into tiny rectangle. Why rectangle? Because it's easy to find the area of a rectangle. So that's what we did for area. We split it into rectangle. We find the area of this plus the area of that, plus we adapt those areas. And the sum of the area gave us what we call the Riemann sum. Okay, so we say that the smaller those rectangle, the better is the approximation. So the more subdivision we take, the better is the approximation. We added the area gave me the Riemann sum, the definition, and that's really gave the definition of the definite integral. Then we introduce a definition. We say that when n becomes very large, those Riemann sum are what we call the definite integral. Fundamental theorem of calculus gave us a tool to compute that integral. That's really the way the whole thing went. Approximate by rectangle, get a Riemann sum. The integral is a definition, by definition, is the limit of the Riemann sum. Fundamental theorem calculus gave us right there. So to be able to compute this complicated area, we approximated by simpler area. The simpler area are the area of those rectangles. We will use very much the same strategy to compute the volume of revolution. But what are the simpler objects we're going to fill this region with? What we are going to fill this region with are simpler solid, and those solid will be cylinders. So what we're going to do, and I will explain, of course. So we're going to fill this region with tiny cylinders. That's exactly what we're going to do. And why cylinder? Because we know the volume of a cylinder. So we're going to fill it with cylinders like that. Find the volume of each cylinder by itself, adding the volumes. This is going to lead us to some kind of a Riemann sum. Okay, so take a complicated region, split it into simpler region. Those simpler solid they will look like cylinder, add the volume. So that will be the strategy we are going to follow. All right, so how are we going to get those cylinder? And that's what's coming up. Any questions before I move any further? So let's see where those cylinders are going to come from and how we're going to do them. So first I want to introduce a word that we use in this section a lot, disk. So what is a disk? What's a disk? A disk is nothing more than a cylinder, but the thickness or the height of it is very, very tiny. So cylinder is nothing more than a very, very thin cylinder. Think a quarter. Like a quarter, that's a cylinder. It's a very thin cylinder. It's like a quarter. So that's my cylinder. That's my disk. Oh, let me use a pencil so I can erase. Something like that. Very, very thin. Okay. So that's a disk. Now what's the volume? So there's still a certain thickness here. What's the volume of a disk? Okay, what's the volume of a cylinder? Anybody remember?
Pi r squared times the height.
Exactly, it's pi times the radius. If this is the center, that's the radius. The radius square times the height. That's the height here, which is a little bit, very small, but that's the height, times the height. Okay, so when I say this, do you imagine exactly this picture? A very, very thin cylinder, no more, no less. So now let me go back to my original problem, which is how to find the volume of a solid obtained by rotating a region around the x-axis. So this is going to be my setting of the problem. general setting, no, setting of the problem. Okay. We have a region R. So we have a function. First, let f of x be a positive function on interval AB. Okay. And we have a solid. Let S be the solid. Obtained by rotating. The region, which is bounded by. So I'm trying to describe the region we're going to rotate, bounded by. The graph of the function y equal f of x, lines x equal to a, x equal to b, and the x-axis by rotating the region bounded by this about the x-axis. Okay. So let me read this one more time, so make sure we understand. So we have a function which is positive on an interval AB. So whatever, something like that. And S is the solid obtained by rotating the region bounded by the graph, the line x equal a, x equal to b, around the x-axis. So this is. Question is, find the volume of S. Okay, so that's really my problem. So let's see how we are going to do it. As I said, we are going to fill it up with actually disk. We're going to fill up the inside with disk. And instead of finding the volume of the whole solid that I have no idea what to do, I'm going to find the volume of those disks that I'm going to fill the region with. So where those disks are going to come from. All right. Can I move? Yes, no, not sure. Okay. All right. So we're going to do it like this. So this is the region. And this is its rotation right there. Right. What I'm going to do is the following. This is A, this is B. I'm going to take this region and do what we did before. I'm going to fill it up with those little rectangles. So I'm just going to take 4 to make my picture clear. Right? And what I'm going to do is I'm going to rotate every rectangle around the x-axis. Everyone's going to be rotated, and I'm going to fill this with the rotation of each one of them. So let's see how the picture is going to look like. So this is the rectangle. I'm going to rotate them here. I rotate the first one. When I rotate the first one, I'm going to get my first disk. I get this disk. And then I'm going to rotate this rectangle. So when I rotate the second rectangle, I'm going to get another disk. This disk. So this one will basically sit. So you have the first disk, and this is really next to it. Then I'm going to rotate that one. So I'm going to change color so to make the picture a bit clear. I'm going to rotate the third rectangle. So that's going to be my third disk. And finally, I'm going to rotate. I took 4 to make the picture very easy for us. And finally, I'm going to take the fourth rectangle. those rectangles. So what I'm going to cover the region with is the rotation of this plus the rotation plus the rotation plus the rotation. That's really how I'm going to cover my region, my solid with. Why rectangle? Because when I rotate them, I get a disk, which is very easy to find its volume. Now, of course, if I take 4, there will be a lot of gaps. So I will not get exactly, I will not fill the inside exactly, but when I start taking smaller and smaller rectangle and rotate each one of them, I'm going to have a disk next to another, and that will be very, very, very thin, and those gaps will actually get smaller and smaller and smaller. So that's exactly how we are going to do this problem. So the way we're doing it is, instead of finding the volume, I'm filling the inside with little disk. And I'm going to find the volume of each one of them. Where those disks are coming from? By basically rotating the small rectangle. So now my object is the following. I need to find the volume of each one of them. So instead of finding the volume of each one of them, I will concentrate on what I'm going to call a typical one, typical rectangle. I'm going to rotate this typical one, find a formula for it, find the formula for its volume, and then add. So we're going to rotate. So step 1, we're going to rotate a typical rectangle. We will get the disk, we find its volume. We will find its volume. So a typical one. So what I'm going to do is, I'm going to focus on one of them. This is my region again. And I'm going to focus on one. Instead of doing everyone, I'm going to focus on one rectangle. So this time I'm dividing into an interval, not 4 anymore, because I want a lot of interval to cover. So we're going to divide AB into an interval. Okay, so I'm going to take this one and I'm going to rotate it. So I will rotate it. The reason I'm drawing 2 pictures because I used one to label and one to draw, because as you realize later on, drawing will become a little bit harder. So this is my piece. I'm going to rotate. And I give me the disk. Okay, now questions. This is the disk I obtained after I rotated. So my question is, we need to find the volume. But to find the volume of the disk, question is, what is the radius of the disk? Typical disk. What's the height? And finally, what's the volume? Right? Step by step. I take this rectangle and I rotate it, I'm getting this disk. What is the radius of this disk? From here to here. Or in this easier picture, that's the radius. Back to you. What is the radius of this disk after we rotate it? Exactly. It's the value, that's f of x. It's the value of the function at xi. It's from here to here. That's the radius. What is the height? Remember, this is a disk. What's the height of this disk? Back to you.
Delta x.
What? You're right.
Delta.
Delta x. So the height is delta x. So the volume of every disk is pi times the radius square times the delta x. That's for every disk. So every time, every one of those, when I rotate it, I rotate this, I get this disk. I know what's its volume. It's the value of the function at x0, pi times the value of the function at x0 times the delta x. The volume of this one, I'm repeating the same thing, but this will be the pi times the value of the function at x1 squared times delta x, and so on and so forth. So now, what is the volume of the solid? How to get the volume of the solid? An approximation of it, the whole solid now. It's almost equal. I am approximating it by the sum of the solid of those disks. It means by the sum of those quantities. So that's the approximation. Okay. So the idea is approximate. We have no other way. We want to find the volume of a complicated figure. We split it into the volume of things we know. And what we picked this time to fill it with are those little disks. So the volume of the solid is approximately equal to that. Now, the larger the n, the better we're going to fill up the solid inside with this disk. So the actual volume is going to be the following. So the formula, as you realize, for this particular scenario is actually pretty simple. So the volume of the solid is going to be what happened to those sum when the number of subdivision become fairly large. It means mathematically the limit of those sums when n, the number of subdivision, becomes very large. Now, this sum here look like a Riemann sum. So if you guys remember a Riemann sum, this will look exactly like a Riemann sum. So if we use the definition of the definite integral, so now that's a Riemann sum. So now by definition of the definite integral, because the definite integral is limit of those sums. Of definite integral, this is going to be the integral of, this is what we're integrating, pi times f of x dx, and then the limit are always which interval you had to subdivide into pieces to be able to cover the whole region with those disks. And this is going to be integral from A to B of that. And that will give me the volume of the solid. So it's an approach that we will be using continuously, which is the idea of to find a complicated quantity. We try to simplify it or to split it into easier tasks to be able to do. So now we have our first formula for today. And you can actually derive it yourself if you go over the lecture, because this is to derive. So the volume of the solid of revolution is given by this integral. I urge you not to memorize the formula. The only thing you have to know is the volume of a cylinder, and the formula will follow very easily. Right? So let us take a very simple example. So the question is, example. Find the volume of the solid obtained by rotating the region below about the x-axis. So I'm going to draw the region and we're going to rotate it and find its volume. So I want a cone. Why not? To get a cone, I have to rotate a triangle. So suppose this is my region. This is y equal to x. And this is 1. That's the region I'm going to rotate. So I'm going to rotate it here. Okay. We're going to get a cone. So my goal is volume of this cone. Let us see what we did. What we did is we're going to fill up this cone by those little discs obtained by revolving those rectangles. So this is my typical rectangle. This is the one when I rotate right here, I'm going to get my disc. Okay. So we focus on a little rectangle and we say the following. Take this little one, we get a disc. Radius of a typical disc. Is the value of the function here. That's my radius. 2 xi. Height is my little delta x. Volume of typical disc is pi times the radius square. Pi times the radius square is actually the area of this base right here. When I multiply it by the height, I'm going to get the volume. That's how I'm getting volume. So that's area of the base right there times the delta x, which is the volume. So now that's the volume of a typical disc. The volume of the whole solid, the volume of the solid, which is the whole cone. So the volume of the solid is obtained by adding those little pieces, which will give me the Riemann sum. So it's going to be the integral of pi. As you realize, I'm not memorizing formula. That's the radius of every piece. The x. And then I go back to my picture. What shall I split into pieces from 0 to 1? And basically of the problem. Now we do a little bit of math to evaluate the volume. Pi is a constant. 2x squared is 4x squared dx. Finally, I will get 4 pi times 1/3 x cubed, evaluated between 0 and 1. And that will give me 4/3 pi. End of the problem. And that will give me basically the volume of this cone. Okay. Any questions? Now today we rotated around the x-axis. So one of you should have asked me, can you rotate about the y-axis? And my answer is absolutely yes. We can do rotation about the y-axis. And I'm going to ask you, I'm going to give you a problem where you have to rotate around the y-axis. And the principle is going to be the same. Instead of taking those vertical rectangle, we take horizontal and we rotate. So the formula is going to be almost the same, but instead of having everything in terms of x, we will have everything in terms of y. Okay. Will this be on the quiz today? No way. What you will be on the quiz is what we did up to yesterday. All right. All right. So you will have your homework on my lab as usual. And now go to Brightspace and start your quiz. And good luck. I'm with you. If you have any question, you put them on chat.